So now let's talk about the extraction of some metals. Well, we talked about the reactivity of metals and we said that not all metals are of the same reactivity. So extraction of highly reactive metals is very hard and it's done through a process called the electrolysis of molten purified ore. And this process is very difficult to handle and at the same time is very expensive. But now we're going to talk about fairly reactive metals and how they are extracted. Well, the method of extraction is the reduction. Wait, let me change the font to make it more clear. Now, the method used is called the reduction of metal oxide with a non-metal. So let's take iron as an example, and you guys have to know this for the exam. The examiner will ask you about this process, so pay attention very carefully. Now, the process of extraction of iron is usually done in a blast furnace. So that's a blast furnace. And also you have to note that iron is extracted from the ore is called hematite and it's iron 3 oxide. And also it can be extracted from magnetite, which is iron 4 oxide. So this is iron 4 oxide. Now, these two ores contain 60% iron. So let's see what happens in the blast furnace. Well, in the blast furnace, coke is added plus limestone, which is calcium carbonate, in addition to the iron ore. Okay. Now the blast furnace has a temperature of 400 degrees Celsius, and this is provided through pumping hot air. So here there is hot air pumped through. Okay. Now the air goes in the blast furnace like this and heats up the process. Now let's take a look at some of the reactions that occur, and you guys have to know these reactions off by heart. Well, the first reaction that occurs is the reaction of coke, which is carbon solid, reacting with the hot air coming into the blast furnace, and this would yield carbon dioxide gas. Now, the second thing that's gonna happen is that the calcium carbonate, which is the limestone, it will thermally decompose into calcium oxide solid plus carbon dioxide gas. Now, pay attention. Well, the next thing that's gonna happen is that the carbon dioxide generated from this reaction will go up in the furnace and react with more coke, giving carbon monoxide gas. Then the carbon monoxide right here starts to go up in the furnace and it acts as a reducing agent, reducing the iron ore. So this is the reaction that occurs. Now, carbon monoxide will react, this is the 3, with the iron ore, giving iron in molten form plus carbon dioxide gas. Now, the last reaction we have to note is that throughout this process, there's some impurities generated, okay? Those impurities react with the calcium oxide produced here, okay? So in the impurities is silicon dioxide in this solid form, and that would give a compound that we call slag. So this is slag. And in the furnace, the slag will be right here, the purple color. And the gray color is the molten iron. So this is the molten iron, and that one is the slag. Well, let's go over this again. I know it was a bit messy, but let's go over it again. Well, we said that iron is extracted from its oxide ores, like magnetite and hematite. In this case, we use a blast furnace at 400 degrees Celsius, and we add coke, limestone, and the iron ore. What happens is the first reaction that occurs, the coke reacts with oxygen to give carbon dioxide. Then, the limestone thermally decomposes to give calcium oxide and carbon dioxide gas. This carbon dioxide gas further goes up in the furnace and reacts with more coke, giving carbon monoxide. And the carbon monoxide is very essential since this gas is the one responsible for reducing the iron ore to become molten iron and giving out carbon dioxide. Now, we said that throughout there are some impurities, and those impurities such as silicon dioxide reacts with calcium oxide to give something called slag. Now, let's see. Well, we said that there are products such as there's here the slag and the molten iron. Well, the slag is often used in making roads, so it doesn't go to waste. It's actually used for something, and we get our molten iron. It's collected right here. So there will be like buckets, or I don't know what they use, but there's something here used to collect the slag and the molten iron. One thing I forgot to mention is that here there are some waste gases, and those waste gases are used to further heat up the furnace. So these waste gases just go right here to heat up the whole process again. So nothing goes to waste. It's an economic procedure. So that's that for the extraction of iron. In the next video, we're gonna talk about the extraction of zinc. So stay tuned and good luck.
Steelmaking. The process basically starts with the production of iron, of which the raw materials are iron ore, coal, and limestone. The iron ore is stored according to origin. Then the various salts are reclaimed and piled in layers on a fines bedding. Before being transported to the next step in the process, the layers are mixed in the rotating drum of a reclaimer to make an optimal blend. Via a transporter rolling over a furnace, the other raw material, the coal, ground to powder, is blown into the furnace. At 1100 degrees centigrade, the coal is now converted into metallurgical coke, consisting of pure carbon with minor pollutions. Removed from the furnace, the metallurgic coke is guided through a quenching station and will, after cooling, be screened into large-size coke, termed lump coke, later on to be used in the blast furnace, and small coke breeze, to be used in the sintering process. Iron ore, coke breeze, and also limestone are now carefully dispensed and blended. This blend is spread on a strand, which slowly moves under a combustion hood. The sintering process. The combustion zone moves downwards through the blend. The high temperature sinters the ground iron ore into a porous mass. As soon as the blend is completely burnt through, it is cooled, crushed, and screened, while the fines are returned to the sintering process. The remaining product is the sinter, the basic component for the next step. The blast furnace operation. Sinter, lump coke, and limestone are, via conveyor belts or skips, transported to the top of the blast furnace. Iron ore is principally a compound of iron and oxygen. Iron is produced by the extraction of oxygen using coke. This reaction is endothermic. To sustain the reaction, extra coke is injected together with hot air. The air is preheated to around 1250 degrees centigrade in hot blast stoves and blown into the furnace through toyers, which are equally distributed around the furnace. Moving downwards, the sinter, coke, and limestone are converted into liquid iron and slag. To save the use of the more expensive metallurgic coke, sometimes pulverized coal or oil is injected. By computers, the process operating parameters are kept under close control. The iron, termed pig iron, is collected at the bottom of the blast furnace and tapped into a torpedo ladle. It's here that the real steel-making process starts. Beginning with a desulfurization process by injecting lime powder. To avoid loss of ductility at high temperature, a sulfur reduction to values lower than 0.010% is necessary. Now the liquid pig iron is transported to the steel plant. Steel making can be carried out in several processes. Nowadays, only the oxy-steel and electric arc processes are relevant. In the oxygen steel making process, the liquid pig iron is transferred into another ladle. The temperature is measured, samples are sent to the laboratory, and the floating slag is removed. The liquid pig iron is now poured into a converter Subsequently, scrap is added. This is to control the temperature increase due to oxidation of impurities, mainly carbon and silicon. By means of a water-cooled lance, pure oxygen is blown into the bath. The impurities are oxidized to slag, floating on the bath surface. Finally, a bath temperature of 1650 degrees centigrade is obtained. At the end of the oxidation process, samples are taken for chemical analyses. Within 5 minutes, the results are presented on a screen in the steel plant. From the analyses, also the amounts of alloying elements and reagents for desulfurization and deoxidation are determined. Alloying elements to ensure a steel composition related to the final properties and use of the steel. By using aluminium, the steel is deoxidized. The steel is killed. The aluminium associates with oxygen, improving ductility. These elements will be added during tapping of the steel from the converter into this huge ladle. The ladle is placed under the converter. Steel and slag are poured out of the converter separately. Tapping, first the steel. After that, the slag. The liquid steel is then stirred using an inert gas, argon. This to ensure composition and temperature to be homogeneous throughout the ladle. In addition, the gas bubbles float out impurities, which are absorbed into the slag. After refining, the ladle, now containing about 300 tons of liquid steel, is taken either to a continuous casting machine or, like here, emptied into ingot molds.
Aluminium is the most abundant metal on Earth. However, it is expensive because a lot of electricity is used to extract it. Aluminium conducts heat and electricity well, has a low density and does not corrode. This makes it very useful for aeroplanes, drinks cans, electricity cables and cooking pans. The aluminium ore is called bauxite. Bauxite is purified to yield aluminium oxide, which is a white powder. Aluminium is then extracted from the aluminium oxide. The aluminium is extracted by electrolysis. In this video, we are going to look at how aluminium is extracted using electrolysis. You should already know how electrolysis works. If you have forgotten, watch our video Electrolysis. How does it work, to refresh your memory. In electrolysis, ions need to pass through the electrolyte, and so the aluminium oxide must be made molten so that this can happen. Aluminium oxide has a very high melting point, over 2000 degrees Celsius. So instead of trying to melt it, the aluminium oxide is dissolved in molten cryolite. Cryolite is an aluminium compound with a much lower melting point than aluminium oxide, and so using this reduces some of the costs in extracting aluminium. The steel case is coated with graphite, providing the negative cathode. The positive anodes are immersed in the molten cryolite and are also made of graphite. Remember that graphite is a form of carbon. When the battery is turned on and electricity flows, the aluminium from the aluminium oxide in the cryolite forms at the negative cathode and sinks to the bottom of the tank. Here, it can then be tapped off as a pure liquid metal. The aluminium sinks because it is more dense than the aluminium cryolite solution. The oxygen from the aluminium oxide in the cryolite forms at the positive anodes. The oxygen reacts with the carbon of the graphite, forming carbon dioxide. The positive anode therefore burns away and needs replacing regularly. This is another reason for the extraction of the aluminium being so expensive. The overall reaction is aluminium oxide to aluminium plus oxygen. Let's have a quick look at the reactions at the electrodes. At the negative cathode, where the aluminium forms, the aluminium ions from the molten aluminium oxide cryolite solution are reduced. This means they gain electrons. At the positive anode, where the oxygen reacts with carbon to make carbon dioxide, the oxygen ions are oxidized. This means they lose electrons. So from this video, you should know that to extract aluminium, electrolysis is used. Aluminium oxide needs to be molten for the ions to move through it, and so is dissolved in cryolite to lower the melting point. The anode is gradually worn away because the oxygen from the solution reacts with the carbon of the graphite anode, producing carbon dioxide, and so the anode wears away and needs to be replaced regularly. Aluminium extraction is very expensive because a lot of electricity is needed.